Okay. I think it's
those are two young faculty.
yeah. Perfect.
Many students.
Perfect. Yeah. Awesome. Thank you.
Okay, hello everyone. Thank you for coming to the curriculum today. We should probably get started with the talk from today. Today we are honored to have Professor Farhan Pograd from Ohio State University. He received his bachelor and master degree from University of Iowa, and he finished his PhD in mechanical engineering from University of Minnesota. That was back in 1990. And after that, he also served as the faculty in the ME department from Michigan State University. He joined Ohio State University in 2015 and became the chair over there after 2017. Since that, his research interest is multi-scale categorization of materials and microstructure-based modeling of forming process, including additive manufacturing, sheet metal forming, tube hydroforming, incremental sheet forming, and thermoforming of fiber-reinforced plastic. His current research is trying to apply machine learning to correlate microstructural properties of metals and fiber-reinforced polymer composites with their antistrophic properties. So we'll welcome our speaker, and as a reminder, we will also have a meeting with graduate student section from 1:30 to 2 p.m. At the conference room of ME 3210. OSU, probably will have some faculty openings in upcoming years. I know some of the PhD students will be on the market soon. So, if you can join the afternoon discussion, that would be great. Let's welcome our speaker.
Thank you. Thank you, Professor Shin. Thank you very much. And I think everybody can hear me with this. Perfect. Thank you for the opportunity. This is a wonderful opportunity to be here in front of everyone, and to be able to speak about your research is always a good thing. We enjoy that as faculty. Obviously, we're kind of used to it. So I thought one of the topics that would be interesting maybe for everyone in here to actually maybe hear it would be this concept of autonomous, basically, manufacturing. My area is manufacturing. And one of the things that has been very pervasive is machine learning, AI, and utilizing those things to be able to actually create autonomous systems that can actually try to operate on their own. So I thought that would be something that I can actually talk about. Of course, the title is very broad, and many, many, many people, as I explained, will be working on these things. And my specific part has to do with the physics-based modeling of certain things with respect to materials, performance, and stuff that goes into these things. Now, this is what I'm presenting is a culmination of a lot of help that I've received over the years with my former PhD students and my current PhD students and postdocs and whatnot, and my colleague, also Associate Research Professor Tae-Joon Park. The cartoon that is shown in there is supposed to actually represent the work that we actually do in my research lab, that is basically thermomechanical processes, which also lends itself very well to the idea of autonomous systems, as I will again explain that a little bit later. But it basically shows that in the past, someone that wanted to make a horseshoe or something like that, it would have a lot of expertise, and they would use their intelligence, their eyes, their feel, and their sense and stuff like that. And they would go through thermomechanical process, heating, forming and cooling and things like that. Why they did that, the goal was to make something, a sword or maybe a horseshoe or something like that, had a certain properties that they cared about, and they thought that it had the proper longevity and things like that, right? So, and of course, at that time, now they don't exist anymore, but at that time, old-time dragons actually existed, just in case if you believe that. But anyway, they provided the heat at that time. So I'm going to try to use this to actually explain what I'm trying to do. So, but before I do that, here's the outline of my presentation. I'm going to give you, as any good department chair will do, is to boast a little bit about their own department and also talk about things that we do. So I'm going to take a few slides to do that. Then I'm going to get into that hybrid autonomous manufacturing process. But then I'm going to whittle it down to what I do, which is the microstructure-based type of modeling of two types of materials, polymer composites, and that are used in aerospace and different applications as well. And also the same thing for metals. And hopefully, if you're interested in a little bit of a materials and mechanics and stuff like that, so that part of it might be interesting. And then I will also explain some of the things that we've done and melded it into a machine learning type of model to be able to then utilize it for being able to actually predict certain things in a very fast and at the same time very accurate way, and then I'm going to try to summarize that. So let me start with my department first. This is basically demographic data for our faculty members. Very similar to here, very, very similar in many respects. We have also, similar to here, 3 groups of human factor and manufacturing, and also we have operations research. And those are basically the assistant, associate, full professors. Those are tenure track faculty, and also professor emeritus faculty in different areas and stuff that are very highly still active in the research and whatnot. And then we also have clinical faculty that is called, these are basically their primary goal is to teach, multiple courses, but research is not one of the primary thing and providing service. And then there is also research faculty that their job is not to teach at all, but rather just purely work on research, and they're very active in that and bring their own money, pay their own salary and whatnot. And basically the total's on the right side and stuff. And we have 8 female faculty and 1 Hispanic faculty there. But we're very proud for a very small department. We have actually 3 National Academy members amongst that. Those are the names. And one of them actually just got it, Antonio Conejo, in the operations research. Got it actually this year. And ironically, each of those 3 are in the 3 different groups. Bill Maris is in the human factor, Conejo is actually in OR, and Alan Lowe is in the manufacturing side of things. Again, this is something that, again, through collaborations and stuff like that, we've been able to actually now do a lot of collaborative work, collaborative research and stuff, and that have basically resulted in increasing our expenditure three times more than before. And that basically means now with opportunities to collaborate on very fundamental stuff, it gives us that opportunity. As far as grad students, we have 66 PhD students and 58 master's students, and that's just a breakdown of the different gender in there as well. And our undergrad students are about 460 as of autumn of 2023, and that's the distribution of, again, between different genders and background. Our undergrad students basically get they choose between 5 different technical basically tracks, and those are data analytics and optimization, supply chain management and logistics, management systems and operation research, manufacturing, and the last one is human systems, basically integration and design. So, and also the faculty research in IEC departments are, again, as I said, in the 3 areas of the human systems integration, manufacturing and optimization, operations research. And you can see under Human Systems, Spine Research Institute is a very large department that is very highly integrated with medical school, Wexner Medical School at Ohio State. They do quite a bit of work, but also we're one of the initiators of the cognitive research from a long time ago, and a lot of graduates from Ohio State actually have been and are professors in different universities throughout the United States, basically. Manufacturing, we look at additive, we look at different forming processes as well as different type of materials, composites, nanocomposites, metals. Also joining is another thing. Ohio State is one of the only places that actually offers a master's degree in basically joining and things related to that, and automation and robotics. And in OR, data analytics, basically energy systems, one of the things that is highly emphasized. Cybersecurity is another area that is highly, a lot of research is done by our faculty. And stochastic simulation and supply chain is the other area in there as well, which I presume is very much similar to here in the department in Wisconsin as well. And there are multitude of, research labs that is very collaborative again. For each of those areas, there are 3 of them being highlighted. That one of them is that Spine Research Institute in the human factor area, and artificially intelligent manufacturing system is another one that is, again, very highly collaborative between everyone, and the last one is cybersecurity and smart integrated mobility. So that's basically a little bit of information about the department that I'm the chair. And so now let's get down to the concept of the hybrid, basically autonomous manufacturing. All this stems from a couple of very large center level funding that we have done, we have obtained very recently. And this particular one is related, it's a 10-year project from National Science Foundation. It's an engineering research center. And the whole idea is to work on the concept of developing hybrid autonomous manufacturing system. So analogous to that, most of us are very familiar with, obviously, with Tesla, with the car company and stuff, and Elon Musk. And you could see that from the left side to the right side, it shows the evolution of automation and getting toward that. And similar to that, you could see the going from no automation as you move to the right. And I believe maybe Tesla has achieved level 4, but certainly not level 5, not at least in a way that it's safe and it's actually reliable. But you could see the level of automation goes that direction. So similar to that, analogous to that, you can look at manufacturing in the same manner. From long time ago, manufacturing was absolutely no basically automation whatsoever. Everything was basically zero autonomy, and everything had to be handled by the operator completely. But as open loop and closed loop, basically controls came about, those levels of automation started to actually become better and better. And we are trying to reach the level as part of this ERC project, the automated level 4, which basically means that there would be multitude of systems that they can automatically and autonomously make decisions with respect to what needs to be done, selection of the different maybe processes, different tools and whatnot in an autonomous way, using a lot of data sensors coming in to be able to actually minimize errors or maybe be able to optimize what the final product is. Now, level 5 would be at a point that obviously we're far away from something like that. There's no such a thing at this time that you basically negotiate with a system that is autonomous. You say, this is what I want. This is the constraints of what it needs to be able to handle with respect to maybe performances of whatever you want to call it, mechanical, electrical, and whatnot. And I want a price point of this. And there would be an autonomous somewhere in a remote place that it actually makes its own decision of what it needs, what processes, what material to be able to actually mitigate that and be able to actually, once it's done, ship it to you and for the price that you do through whatever, Amazon or whatever that you can purchase something like that. We're nowhere near that. We're shooting for number 4 at this point in time. So similar to that, again, conceptually, this is what we have actually proposed. You will have a system, like for example, here shows again a cartoon of that thing, that is basically showing like a system that can be in a secluded place of its own, and what it's basically doing, like let's say that it's trying to get a hip replacement part that it's trying to make with a particular properties that is required and certain texture for, let's say, cell growth and things like that. So in this, autonomous system, there would be multitude of maybe robot hands and whatnot that they perform different things. It could be maybe additive manufacturing, adding certain places, maybe heat treatment, or maybe even forging certain areas and whatnot, followed with a lot of different tools that it can actually utilize in order to be able to do that. And that room basically will be multitude of sensors that is measuring what's going on, and it will basically try to minimize the error between what it starts with, the stock, versus what it's actually trying to do. Something like that will have a brain back here, and you call it a brain, similar to the picture that I showed at the beginning, and that's where the computer is computing the errors and measurement and data collection and data basically analytics on that. And then from here, these are the areas, as I mentioned, it could be autonomously creating, it could be in a surgeon's place that when they're working on someone's replacing someone, it specifically fits their body, their needs and whatnot. And a system like that on the side can actually automatically make that for them and get it ready during the surgery, or if it is in the space and communications is extremely difficult to do that, again, these systems will be able to actually do that. So my research actually is right there on the brain side of it. I work on the ICME part of it, which is integrated computational materials and engineering part of it. So what I do, as I will get into it a little bit, that's my little contribution to the whole thing. So you cannot develop anything, machine learning or AI or whatever that you want to call it, that is not going to need some understanding of the physics-based relationship between things to be able to actually make right decisions, right? That's my job. I develop a lot of physics-based model, but I will try to then condense it in a way that I can create data for machine learning to be calibrated and be maybe even obviously validated, and then going into the design part of it. So these are some of the type of test bed that we will be doing things with respect to biomedical application and using additive plus X processes and whatnot. And even automation, we're already getting to the point that there are autonomous systems that we are developing that actually, for example, if the yellow part is being made, it starts for some with a putty at this point or something like that for low forces, and it goes through its own decision making and actually creates something like that. That's just an example of it. There's a YouTube about this thing that you can actually take a look at it. So that's the gist of this idea. Now I'm going to get into, I'm not going to go too much, and this already was explained, the type of work that I do. And as I said, this is what I'm currently trying to do, develop physics-informed deep learning models that correlates the evolution of the microstructure of metals and polymers to their performance, mechanical, and their anisotropy. And these are some of the fundings that I'm currently working on. And the one on top, as I said, this is the NSF ERC. Also, we do have this one, DOE, Energy Frontier Research Center, that is, again, related to artificial intelligence, but for composite materials. So let me start with the polymer composite itself. And for this, as you can well imagine, there are many parts in an aerospace, in an airplane or whatever, from their engine to their parts within the fuselage and whatever, that require composite materials because of their light, but at the same time, their very strength, their strength is very high with respect to their density and weight. And these things are basically made out of, laminates, which is many layers of materials that are composite, polymers, but also reinforced various way, as I will explain some of that. A multitude of these things are put together, but each of the laminates are made out of ply. And more importantly, down here, the ply itself has, basically basic parts to it that is made out of fiber, matrix, some interface that attaches them together, and that provides what is called a unit cell. A unit cell, if you can work on the unit cell, you can basically then integrate everything upward to a product itself. But this thing is what my work and my research is about. So in this project that we have with the composite materials, the part of it is called digital life cycle development, that I'm the lead on that. We basically start from all the basic things, from little resins that go into it and the chemistry of it and whatnot. And what we're interested, in is basically the effect of temperature, pressure, time, and things like that, how it affects basically the resin itself, as well as maybe the fibers that you're going to put in there as reinforcement, some of the properties of those things. These information that we create and we utilize are input to making some, for example, samples that you can actually test, coupon samples that you can actually test as input. What output comes out of that is going to be some information about residual stresses, warpages, and things like that are there. And with respect to the volume fraction, void volume fraction, and degree of crystallinity that comes from doing these things, temperature, pressure to it. So these things are basically fed into each other, different level of physics-based model that you input something and you get an output. Then that goes to the next length scale and next length scale. So for example, the output from these understanding, degree of crystallinity, density, and things like that, goes into something that is in the middle called the RVE, or representative volume element. That this is what I described at the very bottom of that diagram. The previous diagram is where RVE is, and it will have information about the matrix as well as the fibers that go in there. We then use this thing as the output of this will go as input to the macro level finite elements and whatnot to look at maybe things, engine part or whatnot. There's also in the whole thing, there's also uncertainty quantification. There are variability in everything, in properties, resin, in the process itself, that needs to be quantified and needs to be brought back into affecting these things. So if you have predictability, you want to make sure that how does that affect? Because your model can be very perfect, but reality of life is not. Now, as I said, my area is actually more focused in the middle of those kind of things. So when we talk about these fibers, we're actually talking about different type of fillers. You can have fiber fillers, you can have biofibers, you can have nanofibers that are actually introducing these things. They all have different effect that needs to be understood. And of those, ultimately, what we measure, for example, in mechanical is stress versus strain, which hopefully everybody have seen that before. So for example, a material that is the red one that has a higher elasticity, but it also maybe breaks a little bit faster than another material that is maybe the nanocomposite in the middle or maybe polymer. These are the things that any model, whether it's a machine learning or whether it's a AI, needs to be able to mitigate, needs to understand, needs to be able to predict in order to be able to decide autonomously which combination do I need to use in order to make a sunglass for you at a price that is given to you and whatnot, right? So these are just the little components of everything that needs to be brought together in order to create an autonomous system. We also look at different type of fabric reinforcement. You can have two-dimensional fabrics that are woven like your clothing and whatnot that can go into these things, and also three-dimensional type of thing that are knitted material. And these things all are important as part of this project to have all sorts of data provided to a machine learning to see that it can then pick and choose, because each of them perform differently. So for example, if you have putting these things into a model of compression molding or something like that to make a helmet, that helmet, you want to be able to predict what type of strength does it have to mitigate a bullet or be able to dissipate the energy and whatnot. So you do not want to make it and then try it. You want to basically be able to predict these things, and to be able to have a good idea of predicting these things requires step-by-step progression of building this thing to that point. Now, even in additive manufacturing processes, as you can see, there are many things that are there that affect of the heating, cooling that happens every time that a material is melted and laid, and then it cools, and it goes through a multitude of these things because layers that are below are also getting partially heated and cooled as you build a part. So these are the things that needs to be developed and put into a model. Here's an example of nanocomposites, that how do we actually melt the data that we collect from an actual part, and how do we basically create a digital twin of that to be able to actually create the data that then we don't need experiments. So for example, we have, these are nanographene platelets materials that it actually put inside of a polymer composite. We use basically what is called FIB, focused ion beam, to slice this thing into small, few micron thin, and you can see there are layers of it. And if you look at any of these layers, you can actually see these nanographenes that are actually going through. And what we are interested in is the statistical information about this. For example, the distribution of the diameter. So they don't have the length, and diameters are not always the same. So from here, you actually can collect that kind of a data for the material. And also, what is their orientation? Which direction? What is the distribution of the orientation in there? As well as also, what is the volume fraction? So we looked at 2-point correlation functions to be able to get information about what is the volume fraction and what would be, for example, the distribution of that as a function of the size as it becomes bigger with respect to these arrows that is put in here. So as an example, this part is shown in here in black and white, so you can see only the fibers, and you can see that they have a particular orientation. So if you actually did the 2-point correlation function along this 0 direction, it would be back here. That's the volume fraction stays the same, but the distribution will be very different. If you do it at different angles, you get different properties, statistically different properties that come out of this thing. This is characteristic of the material, and because if this material was completely homogeneous, randomly distributed, all these basically curves would fall on top of each other, and there would be only one curve. So by having different curves, that means this material is highly anisotropic. And as a result of it, it needs to be mitigated. So what do we do next? For a mechanician myself and the data that is provided, I want to create a digital twin of this, something that is statistically represents what I have. Why would I want to do that? The reason is very simple, because then I can do more physics-based simulation on it, and I can create a lot of data from it, and even variations of it that I don't even have to run the experiments anymore. Makes it cheaper, faster, and I can create data, right? So to create from these type of statistical data that we can hear, we go through an iterative process of generating these type of basically representation that has, we use a code that is called Dream 3D. That thing goes through thousands of iterations, and it basically puts these different platelets, or you can put different kind of spherical or whatever that you want in there. But what it does, it creates these things, and then it checks the properties of them as if it does a 2-point correlation test on it, or it looks at the distribution until we get the same match with respect to the size, and also with respect to back here. You can see that it reconstruct. That's a reconstructive process that's very tedious. But once it's done, now we have a geometrically identical property, statistically the same as before, right? Now what? What we want to do at this point, we're not done yet. This could be water and potatoes in there. You need to say this is graphene. You need to say how does this actually adhere to the resin itself? So now we get into the mechanics part of it. So for the resin, we know that this material is like a glue, but when you heat it and cool it, it changes what is known as crystallinity of it or something like that, changes properties. So we take care of those, what we call viscoelastic material, Maxwell models and stuff. We put that in there to represent anything that is in there as a glue or the resin part of it. We then put fiber properties in there because if it is fiber or if it's graphene, we put the property in there. But more importantly, how do these things actually attach to each other? What is the strength, the bond between them? You wouldn't know that until you do some simulation, atomistic simulation called molecular dynamics. We do that, and we actually put these graphene platelets in there, and we actually pull them out and see what the properties, the strength is in order to pull that out. Then we put that information into these type of model that actually has the platelets, has the matrix, but also it has the strength of the bond between them. Now we have a complete model. We have a twin version of this actual process, statistically the same, and also otherwise is the same. Now I can do all sorts of tests on it, not just tensile tests. I can shear it, I can squeeze it, I can do whatever to it. One thing we have found out is, in fact, we can do sensitivity analysis, and what we found out that depending upon the aspect ratio of the size of the platelets and its thickness, we can do testing on it, and we can find out that, in fact, if you go beyond a certain aspect ratio, in fact, your property will be even less than the actual pure matrix. So you have actually defeated the purpose for that. And we can do a lot of different type of testing on these, and we can now utilize that even in a machine learning situation that now you understand is I can take these data and train a machine learning to be able to actually utilize it without even running any of these tedious type of things. All right, so here's 3D printing. We found out that when we actually do a 3D printing of a box shaped like that, and when we actually take sample, dog bone samples, they call it, to do tensile testing in different directions, like X and Z and the plane of X, Y, and XZ, their strengths are completely different. It makes sense. Why? You look at it, and it's printed, it's nice. You don't see with your visual eyes there are holes and porosities in there, but there's tremendous amount of those things in there that you don't see, and those things affect the properties. How the pattern of laying those things are, they lay it and they build it up, is going to affect it. And again, that's exactly what we do. So we created, again, similar to the preform, we actually use micro-CT to look at these, and we reconstruct basically what the void distribution is. So you see a complex thing red in here. This is actually void in a printed part. We need to take care of that in our models, and we create an RV. So once we create this thing from image processing that takes a lot and has all sorts of data, statistical data about it, size-wise and the distribution and whatnot, we then create an RVE of that. This is the void itself. This is a RVE which has the other part of it, the resin part of it around it, and then we know what the volume fraction is. We can create something that looks like this, that has exact statistical equivalence, but it doesn't exactly look like it. But we can then do the testing in X from this X direction, Z direction, X, Y, and XZ, similar to that. And we can go through a process of calibrating the parameter of this RVE that represents this type of printed material. Once we have it, again, we're generating a physics-informed data that is there. What do we do with the AM process model itself? AM process, as I said, goes through a lot of heating and a lot of cooling, and that also is of interest to us. Why? Because once this material goes through heating and cooling cycles of these, it actually changes property and it creates residual stresses. We take that information from this process and we incorporate it into here to be able to actually then have even more accurate, more precise data. And again, once you have an RVE, you can create a lot of data. So this is all steps toward those data generation. By the way, the Part DLC platform, what it does from our model, the output of that goes into a a machine learning model. And what they do is they create basically a VAE, a variable auto encoder, that the data that we generate, as I just mentioned from those RVEs, it correlates that with basically the performance of that. So these are different layers of that basically machine learning, has all the statistics incorporated in there. So now we have an VAE for the material itself. We also have, as I mentioned, manufacturing processes that basically says how you process it, whether it's additive with beginning and end and whatever size, nozzles, heat, speed. That also is another one that is a VAE for additive manufacturing. And again, that creates the relationship between input and output of these things. This is not done by me, not all of it, not by my group, but another group of colleagues that we have in different universities. The output of that goes into another AI-enabled inverse design that takes the inverse, takes these VAE models, and basically says, if this is the process that I'm going to use, 3D printing or whatever, I want the output to be this. Basically, the inverse of these things are being incorporated to say, if I want with this process to have a particular property, what should be my material and what should be my process parameters to do that. So this is where the inverse design and iterative design will occur as the next step. So this is where the connection between physics-based model goes into a machine learning type, and machine learning goes into an inverse AI-enabled type of work. Now let me talk very quickly about a little bit about metals. Metals are just as difficult, if not a different beast, when it comes to its behavior, and that's some of the things that interest me, and I try to actually give you a gist of it as well if you are interested in these things at all. But metals themselves, when you look at it under a microscope or something, the way that they're represented is with these cubes that show different grains. Now, you could see that there are different grains in there, and I will tell you what that meaning of these colors are. Colors are basically talking about cluster of atoms that are oriented in a particular direction. For example, red and blue means these are clusters of atoms, but they're oriented in different ways, but they're all come together to create one material. Now, if you look at these things in this platform that is called basically like looking at the inverse pole of this thing, if you get these circles that is completely the same color, that means this material is completely homogeneous. It's like property is in every direction the same thing, okay? Now, representation of this in a mechanics, in a stress space, is a beautiful oval shape in stress space that whenever you see an oval shape like that, that means this material is completely isotropic, behaves the same way. Now, you go through material processing of any kind, rolling, forming, forging, whatever. As soon as you touch the metal, that metal starts to change shape and directions. It becomes elongated, it becomes compressed, and it will have different color. As soon as you do that, that creates anisotropy. So this becomes something that has different distribution. And these colors basically shows the number of, or basically the concentration of particular orientation that is created within this. This shows everything is the same. Here shows there are different distribution of those things. Now, if you plot it in a stress space, you could see that it doesn't look like oval. It has some sharp edges and things like that. And that basically tells you that this material. Now, in the world of people that work with metals, they have to go through a lot of like rolling. They get the final product out, and they have to cut a lot of samples out of it to be able to find out, are these things isotropic, not, or whatever. And they go through this process, which is very difficult experimentally. And in other type of form, to be able to get other type of properties, for example, the strength of it and formability of it, they go through all these type of tests. Super expensive and incredibly time-consuming and not easy to equipment. Now, the problem with that is as soon as you make a little bit of change in this process, this will change, and all of these things have to be repeated. And that's how expensive things are, right? So we want to avoid that. And I'm not going to get into this thing, but I would say that we can look at these microstructure and we can look at the mechanics of it. And one of the things is these clusters of atoms that you see in here, they actually move a certain way along a certain plane and direction. These mathematical equations basically covers that. And this is the fundamentals of metal forming for these type of materials. I'm not going to get into it, but what happens is this. that now that going back to that, like let's say this is a tube, and if you measure in here those clusters, it has different types of colors. Now, each of these colors with respect to this nice cube back here, they have different orientation. They're the same thing, but they're oriented differently. And that field that I showed in stress space for this red color looks like that. If you go to the green one and blue one, you can see that they're a little bit different just because their orientation is different. So this material itself, if I'm interested in knowing what is its property, you could see that if I look at 5 of these, or you could see in here there's 10 of these, homogenized in here, I would get something like that. If I do 50 of them, it starts to actually, and this material has several thousand, 5,000 of them. If you go to 500 of that, more representative of this material, that thing is starting to evolve, but it's never going to look oval shape as it was originally before. And if you go to 5,000, it eventually settles to that. That last one in that stress space represents that particular material. So if you change that, you can get different properties that behave differently. So this is what the capability offers to us. We work with Sandia National Lab, and they actually took this thing and they took measurement on the surface of it in the XY plane and YZ plane and XZ plane. They got all of these things with tiny, tiny little things that are about 7 or whatever millimeter, very small, and they did a very tedious testing on these things. They measured these. These are basically those texture that I was talking about, highly anisotropic. What they found out from these tensile testing that none of these things fall on top of each other, which basically means that this thing is highly anisotropic, not isotropic. And they also measured some other factors called R factors that, again, shows they don't fall on top of each other. That means highly anisotropic. What we did with our model, we actually took those things from 3, and they created, going through that statistic, and created one that represents exactly the same material as that tube. We tested it. Here's the actual measurement. This is what we actually created from here. And it actually did pretty good comparison. So again, this is important because it allows us to be able to trust our model. Even in that, we realize that, for example, here the trend is not correct. That even told us something with this model is not enough. That needs to be done. And we realized that they only measured these things basically afterward. This is a tube that it was extruded. They just said this is what it looks like. But the tube itself went through a process to get to that point. That created certain deformation in it, residual stresses that we did not account for, that this doesn't. So what we did, we created an optimization, basically, model of this. We said any material before it became a tube must have been completely isotropic. They measured this thing at the end when it was already a tube. They didn't know anything in between. But we understood what an extruding process is, so we created an optimization process that we said if it starts from here, what type of parameters of deformation it must have gone through in order to be able to actually get the final one, which is here. So we did an iterative process to actually figure out the parameters of deformation. Once we did, this gave us the residual stresses. We then created another model, which we call optimized model. So this is the original one. I mean, this is the EBST, the original experiment. This is the sample without that. This is when we put actually those residual into it. It starts to become a lot more like that. And then when we use this model, it actually predicted things. This is a sample texture just to optimize. We could see that actually it did correct even that error. All of these models are bringing you more and more into trusting the data that you can actually create. We actually developed another model of that even faster than that. I'm not going to get into details of it, but this is what actually did the job for us because it was basically a model that is 1,000 times faster without really taking advantage of certain deformation, but still looking at all the microstructure. And this thing actually was very good for us because that allowed us to be able to do the next thing, which is developing a deep learning neural net for that. But before doing that, we also looked at, for example, here's the whole thing that you start from anything that that starts with, and then it goes through a manufacturing process in here, tube hydroforming. It goes through some heating and cooling and all of that. it changes properties, and then we can actually recreate new, basically RVEs that we can then test it and be able to tell that process what does it do to it at the very end of it. Now, again, as I mentioned, this is all to be able to create a trustworthy machine learning type of model based on these things. And what we did is basically, we know that these little green, red things that I showed you called texture and orientation of these things. You can literally create, you can basically come up with 3 parameters that gives you any type of orientation that potentially could be available to any kind of a metal. So what we did is within that space in 3-dimensional, the cloud, the red cloud that you see in here are points of those orientations that we actually took from that, all sorts of combination. In fact, we generated 75,000 data points of these orientations. And then we ran our model with those things, with those initial texture, and to see what at the end of it will come. What we got is about 4 million data points. But we did this thing, instead of, it would have taken us maybe a year to do that thing, or not more than that, within a few days. And once we had that data, we basically fitted it into a neural net model of that basically says, if you know what the original texture is, what would be the mechanical properties of that? In a very quick way, we used the 54,880 of it for calibration, but the other 20,000, we did it as validation. And validation basically looks at the error between what you fit and what you actually have down here. And the biggest error that we had was less than 1% that in the total. So we truly could trust that. Now, what does that all translate to? Very simply put, we even did some simulation of this thing with a neural net model or with a very extensive physics base and even with the fast one. And in every sense, it actually captured it very well. But the important thing is we worked with our colleagues at Sandia. They created a website that people can literally just give the texture that they measure, one texture, whatever it is. They provide that texture and as a file, and they specify whether this is a FCC or BCC, like aluminum or steel or whatever. And they also ask which type of parameters that you need for your macro level model, which parameters for which model that you want. You specify that, and literally what it does, you put your information there, your texture, and it immediately on an instantaneous basis will give you what the properties will be, what the distribution would be, and even the parameters pops it right out. And you can take that in, if you're a mechanical engineer or something, you put it in these parameters into your model representing that, and literally you can then proceed. This procedure would have taken maybe a couple of years to do this thing experimentally. Now you could do it in a flash of an eye. You can actually do this thing, and thanks to that. So let me finish my talk by just simply saying, in this domain of work that materials are needed, obviously, to make anything, if you rely too much on the physical experimentation, expensive, time-consuming, very accurate, though, because you're actually literally doing it, but the speed is terrible. If you use the type of model that I talked about, high-fidelity type of model, it's a little bit better speed-wise, but accuracy is still very good, but it takes forever. If you use none of these things and use simple commercial codes and assume everything is like homogeneous or whatever, high speed, but accuracy very low. But the type of things that we developed based on this that eventually lend itself to a machine learning, it has both the accuracy and the speed, and therefore it's a step toward that autonomous thing that we want to do to be able to actually have a copious amount of data that it can actually select from and know the relationship between these things. So with that, this is just a couple of summaries and stuff like that. I don't believe the last one is that the first function in autonomous manufacturing system is still long ways away, but maybe someday we'll get to that point. But these are just one little piece toward that. So with that, thank you, and if there are any questions. I know I covered a lot of different things, so.
Yeah, Thank you for the interesting talk. One question is a common challenge in machine learning used for the material discovery or the prediction for engineering system is lack of data.
Right.
Is in your model, in your development, no matter for the metal-based prediction or for the polymer-based prediction, right. Typically, how large is the data set you have, like from the experiment? Is 100 specimen?
Maybe hundreds,
okay.
maybe 1,000 max or something like that. You can maybe collect from experiments that have done. Typically for the mechanical testing, they do a lot of these dog bone testing, and they collect maybe force displacement, stress strain, or maybe some strains or something like that out of it. But that's basically the total they get. Now, therefore, there's not a whole lot of data that you could use. So, and I agree that if you don't have enough data, how do you calibrate or how do you even validate under different cases? So what I was showing was the fact that we're trying to mitigate that by trying to do a lot of simulation. We know we have limited amount of data. We know that. So therefore we're saying, and we know that how expensive and tedious it is to create more data. And especially certain cases of deformation are literally impossible to do testing with good control. So that makes it even not possible. However, when you have a digital twin of that, you are then, if it is calibrated and statistically represent exactly what you have, you can do all sorts of deformations that are not even possible, generate a copious amount of data. That is the beauty of this, that it allows you to fill the gap where it cannot be done experimentally because of expensive and lack of capabilities and all of that. So I think in this regard, we're just helping with that aspect a little bit. Yeah, but you're right, absolutely. We need a lot of data.
Okay, thank you.
Hi, thanks for the interesting talk. I'm curious, in some of these machine learning prediction models, like for example, the online one where you could just unload that and you get a prediction out, does it also give any sense of uncertainty quantification around the prediction as well? Is that something that comes with that?
It does not. It does not have it, but what we can do if we artificially introduce those things, some variability, statistical variations in those things, that will allow us to be able to actually then find upper bound, lower bounds, or things related to that. So we can introduce those things as an after the fact, right? So you could say that maybe this is the median or average properties, but we know that there is variations in here with this type of distribution. We can actually put all of those things in there and run again the model and find out what would be the effect of those type of things. And that way we can maybe, have some quantification of those things as well. So I don't know if that answers the question.
Yeah, good, thanks.
Okay.
That's actually my question. Yeah, you steal it. But I think another follow-up comments is once you have the quantification, it can be used as inputs to decide how could you conduct experiments, because experiments takes time and money.
Right.
So using those as certification can give you a guide to be more smartly. Right.
Yes.
Yeah.
Excellent point. Actually, this could guide what kind of experiment we need to do so that we don't waste our time in some respect. Right. Absolutely. Very good point. Yeah.
Any other questions? One question I have is, for process, driven based, development, a lot of times the, framework that you develop for one process is hard to, use that to a different process.
Right.
So
Right.
most time we have to do all the, experimentation and validation one more time, and it's.
So that's a very good point. And we try to actually make this thing as generic as possible, right? So going back maybe a little bit to composites, but first of all, for this one, it's atomic structure. If you use FCC, like aluminum and copper, or BCC, which is steel of different kind, this application, as I said, even once we develop this thing, in that site at Sandia, you just need to specify, you just need to tell us, this is FCC or BCC, and this is, and it applies to all of them. Now, let me go back to composites. In the composite part of it, as I said, again, what we're interested in is really down here. I don't care the ply or what the constituencies of these things are fiber, some reinforcement, some resin, and some interaction. this is the unit cell, the lowest level that you can actually get. I use the same thing, whether it is a forming of layers of these things, or whether even the same material model goes into this. It's the same basic of interaction between a matrix and some sort of reinforcement, or maybe some different phase, like a void or something. So this is general enough. So even if I go to the next one, here you could see that we have, for example, the same void could be from 3D printing, but if the void is known, this RVE could be for a fiber, or it could be for something that has just being printed by this process. So it's almost like irrespective of that. We go to the most basic aspect of it, from a material aspect of it, and then we assume that the same kind of things apply, whether it's 3D printing or fiber reinforced stamping and things like that. I don't know if that answers your question or not. So that's why it's more fundamental to not be worried about, oh, it's only for this. Certain aspect of it is. I mean, certain aspect of it, this void is maybe only for a certain type of printing. But I can change this in this model. I can change the characteristic that without even running any more experiment. If I know from CAD, this void approximately is this, or volume fraction is something, I can make another one with the same thing that statistically fits it, and I can say the property of that part 3D printed in a different pattern will be this.
That's a great answer. And the other question I have is related to a kind of real-time concept for autonomous based manufacturing. How to make everything to be in real time would be critical. How do you define real time in all of that?
None of these are real time, obviously, and that was my point, that the only thing we can do, these are very time-consuming models to run. This is just giving us enough confidence in the model being fundamental. Now we use this thing to generate many, many data that needs to be then captured by a machine learning model, some regression, something like that, that it captures those things. Now we don't need to run it anymore. So that the part with this part, really, this part, whatever we generate, this data is an input to this type of VAE type of model that gives correlation between whatever resin I put in there and pressure and whatever, and this is what we get. These things are coming from up here, right? These type of things, we put it now in here as an input-output relationship. Also for manufacturing, we can create a VAE. Now that you have this thing, that's a correlation, it's a fast-running type of thing, then it could go even into inverse model of saying, I want this with this type of performance. Can we solve the inverse problem of this, knowing these correlations, and be able to? So of course, we had a discussion, some of these, if it is very simple processes, linear processes, yeah, it works very well maybe. But if you go into situations that very highly nonlinear, or the material has some sort of a muscle memory, or if it remembers certain thing, it is path dependent, these things might not quite work, these simple VAs or something. It might need some sort of maybe advanced way of bringing that PDE into it, or physics back into it, to be able to even bring some nonlinearities and stuff into these type of predictability. But ultimately, as I'm saying, this is too time consuming. We need to then create data from there to the next one. Okay.
Any other questions? Okay, if no, let's thank our speaker.
Thank you. Thank you very much.
Yeah. Again, from 1:30 to 2, there is a meeting with graduate student section at the conference room. So thank you all for attending.
Thank you. All right. Well, hopefully it wasn't too boring.
No, I saw my students here. We are trying to tackle the real-time challenge.
Right.
Of that.
I think that part really ultimately comes to that, developing machine learning. You're just creating data that is not possible to do experimentally, too expensive, and as I mentioned, you make one little change in the process, you have to repeat these macro level testing to be able what it is. But if you have this kind of physics-based model, once you develop it fundamentally from very basic level, then you can change those things in there. You don't need to go and run the experiment. So therefore, you can generate copious amount of data, and then that's it. I mean, as I showed with that, we looked at 75,000 data we generated. It covers all the different type of material. I don't need to go and do it one by one. Once we did it, we generated enough data that it went into that neural net, and now they just say, in that website, here's what I have. This is the texture. That's it. Boom. It gives you everything after that. You don't even need to go and do anything. Yeah. So I mean, that's where the thing is, I guess. So let me.
There's so many icons on your desktop. How can you
I thought my desktop was messed up. But
No, I'm sorry. My
decoration?
no, I wish it was. No, but unfortunately, each one of those things is something that I know where they are, or something at least. So this is an old computer. Actually, that's why I had a little problem getting it going. I think sometimes it's like, leave me alone. Let me retire.
I can take your luggage back to my office, and then you can have a look.
I appreciate that. Thank you. Thank you. Oh.